Hello everyone, and welcome to the first webinar for 2020, which is Modelling Geosynthetic Reinforcement with LimitState GEO. I'm Tom Pritchard, the host for today's session, and I'll be passing you over shortly to our speaker, who is Dr. Colin Smith. Hopefully today you'll come away with an overview of how LimitState GEO's engineered element material works and how it can be applied to problem types that involve geosynthetic reinforcement. The webinar itself is going to run for about 45 minutes and should include a few minutes at the end for questions. You can post these at any time during the webinar using the functionality that should be present in the interface in front of you. We do try to answer as many questions as we can within the webinar in the time available, but this isn't always possible, but we do reply to all questions that we don't cover over the next few days via email. So, without further ado, I'd like to introduce you to our speaker for today, who is Dr. Colin Smith, and he's the LimitState GEO Product Manager.
Thank you, Tom. Okay, as usual with these webinars, I'll start off with a few slides just showing you the range of modelling capability of LimitState GEO. It's a very general purpose ultimate limit state software product able to determine the collapse state for any problem geometry, and it can model slopes, retaining walls, structural elements and soil reinforcement as shown in some of these examples. Today our aim is to look at modelling geosynthetic reinforcement. So we'll first say a brief introduction to LimitState, the company, then say a little bit about the background theory to reinforce soils, geotechnical analysis software in general, and then look at how we specifically model two-dimensional geosynthetic reinforcement in the software, and wrap up with an example on a reinforced embankment. So I'll be using the software directly to illustrate the key points, but I'll make use of a few slides throughout the presentation or the webinar to introduce key concepts and give a summary. So first we'll look at LimitState itself. Our mission is to provide engineers with powerful software for ultimate limit state analysis and design, leveraging the latest state-of-the-art algorithms and optimization technology. And this innovative approach has generated a client base covering over 30 countries worldwide. So where does this software fit? Well, we focus on tools for ultimate limit state analysis, so that allows us to provide products that combine speed, ease of use and simplicity of the traditional methods, but we've got the flexibility of finite element type methods to handle any problem geometry. Because of this ultimate limit state analysis, the only core parameters we require are cohesion, friction and weight of soil. So that's enough introduction to limit state. Let's look at modelling soil reinforcement. So as I'm sure you all well know, soil reinforcement works primarily by adding tensile strength to the soil, or equivalently by transmitting load from one part of the soil body to another. And soil reinforcement can be one-dimensional or two-dimensional, so it includes soil nails, steel strips, geogrids and geotextiles. And it can be used in a wide range of configurations for slope stability as part of a reinforced soil wall, or for example to support an embankment on soft ground. Now in terms of the analytical approach, conventional approach to modelling reinforcement, if we look at standard textbooks and design codes, there's a general consensus on the general principles of modelling reinforcement. So either the reinforcement pulls out of the soil, so if we had a sliding wedge along this boundary here, and that wedge slid, this bit of reinforcement would pull out, or conversely, as if this wedge slid down, this bit of reinforcement would pull out of the wedge. But essentially the relative interaction is the same. It can be modelled in a general way. So if we're looking at a wedge type analysis, for example sliding on that plane, then essentially we do a classic sort of Coulomb wedge calculation, but include additional forces acting along each line of reinforcement equivalent to the pull-out force that is available in that reinforcement position. Excuse me. So determining these pull-out forces is one key element in the analysis, and the normal approach that is taken is that for an undrained soil, it's assumed that the shear stress at failure on the reinforcement boundary is equal to some factor alpha multiplied by the undrained shear strength. And alpha is an adhesion factor, and if we're working with two-dimensional reinforcement of length L, then the pull-out force per unit width into the diagram is 2 alpha CUL, the two bringing in the shear on the top and the bottom of the reinforcement. For a frictional soil, a drained soil, typically assume that the shear stress at failure on the boundary is the normal stress multiplied again by some adhesion factor alpha multiplied by tan phi, where phi is the angle of friction of the surrounding soil. And so again, the pull-out force is going to be given by this equation 2 alpha sigma n tan phi, again 2 to cover the friction on the top and the bottom of the reinforcement. Now, in hand calculations of horizontal reinforcement, the average normal stress is typically taken as the weight over overburden at depth per unit area, and doesn't account for any stress changes in the soil mass that are due to sliding failure. So there's an idealization in that type of conventional analysis. So we'll look at how this type of modelling concept is applied in LimitState GEO, so that we capture the same principles but in a very general way. So before we do that, we'll have a look at how the software works, so we can contextualize that. So LimitState GEO operates its key enabling technology is discontinuity layout optimization. And we'll just recap quickly on how that works. So if we have a domain here, which is a rectangular block of soil with a load on it and fixed boundaries to the left and to the base, what we do is we populate the domain with nodes. It's not an element-based method, it's a node-based method. In this case, we've got an array of 4x3 12 nodes. And in principle, we connect every node to every other node with a potential slip line, and then we utilize optimization to pick out of that set of potential slip lines the critical mechanism that dissipates the least energy. And that gives us our critical collapse mechanism. So for 12 nodes, we have 12 times 11 over 2, 66 possible slip lines, and using optimization, we pull out the 6 critical slip lines that form the collapse mechanism. Now, the more nodes we use, the more accurate the solution, and typically the software would be running with 500, 1,000, 2,000 or more nodes, and millions of potential slip lines to be modelled. So in the context of reinforcement soil interaction, this means that adopting this approach we can capture several different modes of that type of interaction. So looking at this diagram, we've got an analysis which is showing several wedges of soil sliding around the reinforcement. So at this point here, you can see the reinforcement in the animation being pulled out of the soil, so that's modelling sort of classic reinforcement pull-out. Over here we have differential movement between the soil and the reinforcement along the length, but that is also captured correctly. And further down here you can see that the reinforcement is staying embedded in the soil behind the wedge, but here it's being pulled out, and we've allowed it to pull out of the wall element in this case just to illustrate that point more clearly. So the software is able to capture all those classic modes of behaviour and combinations of those modes with its very general model. Now, software has been verified against a wide range of closed-form solutions and benchmarks, and every time the software is run, we run thousands of tests to make sure that the software is doing the expected thing. and over 100 of those results are available on our website. You can look at them at LimitState.com geo/verification. Just got one graph here showing a reinforced embankment problem comparing results of DLO to results in the literature, and we get a good match generally for most of these comparisons. A lot of papers have been written using DLO, and you can find that on our website. So if you go to the website, you can download a bibliography which lists all the papers that have been published looking at a whole range of problems from slopes, bearing capacity, retaining walls. This is just a snapshot of a section on reinforced soil. So that's a background. We're now going to look at how we model the actual reinforcement in LimitState Geo in 2 dimensions. So the software has a specific element within it called an engineered element, and that can be configured to model 1-dimensional or 2-dimensional reinforcement. The way we're going to look at one way of using this element to model 2D reinforcement, which is to use this engineered element with a 0 bending strength, and with that element it's able to transmit tensile forces along its length, but it's also able to accept shear stresses along its boundary, and we can specify different interface properties on the top and the bottom of the reinforcement to allow for those alpha factors that we discussed earlier. The analysis will inherently determine the normal stresses on the boundary, so those don't need to be pre-calculated, and also it will allow differential shearing above and below the reinforcement so that you can, for example, model the case where you have soil sliding on the top of the reinforcement but the soil below stays fixed. And so it's able to capture a whole range of phenomena, pull out, sliding on the reinforcement by the same model essentially. And so because it can seek out the critical mechanism, it can seek out also the critical interaction with the reinforcement without having to predefine where areas are pulling out or sliding. So before we go into that, what we'll do, we'll now have a quick look at an element test, if you like, in the software, just to show how this 2-dimensional reinforcement works. So I should just bring up the bear with me, I shall bring up the example file. This one. Okay. So here we have a block of soil. This is a clay soil above and below the reinforcement. This red line here is the reinforcing element. We have a block of a rigid material here in which we've embedded another reinforcing element, and the reinforcing element is connected to the one in the clay soil. And the reason we do this is we want to be able to pull this element out of the clay and see what forces are built up on the clay on that element as it's pulled out. So with this rigid block here, we apply a load to this face here, and that load is specified in such a way that the result that we get from the software tells us what force is required to pull this reinforcing element out of the clay soil. Now, for those of you not familiar with the software, I'll give you a quick overview of how it works. So on the left we have a number of buttons which control the display or the drawing of the geometry. Up here we have standard sort of save, open, etc. We've got a materials explorer here which allows us to define different materials and apply them to the model, and this property editor on the right, anything we click on in this domain, we get the properties here, so it's very quick and easy to edit properties. So if, for example, I click on, if I click on this body here, it will tell me immediately down here what the geometry of that is, so what the dimensions are, and it will also tell me a number of other properties. We won't go into all of them at the moment, but one of them is a material. It's a clay that we've defined, and we're going to work with its undrained strength, which is an undrained strength of 50 kPa. And in that we've got this reinforcing element. If I click on that, we can see that it runs from 2 to 3.5 meters length, so it's 1.5 meters long. It's embedded in the clay, and the properties that we have can be found here. And the engineered element in the software is quite a flexible element that can be used to model a range of things, as I mentioned earlier. So some of the properties that are modelled relate to one-dimensional reinforcement, such as soil nails, which are mainly these factors here. So we can just ignore those. Main thing is that we need to set this value to essentially infinity. In the software, you use 1e30 to define infinity in that value. And then we can set a moment of resistance, a bending strength. So actually for a reinforcement, we'd normally just set that to 0, so there's no bending strength. And we can define a rupture strength. Here we'll just stick with infinity, and a compressive strength. So again, flexible reinforcement normally has no compressive strength, so we can set that to 0. That defines the reinforcement, and we can then run the simulation by simply clicking this solve button, and that will essentially tell us what load is required to pull this out of the soil. So I click run, and we get a very simple mechanism where this rigid block of material pulls to the left, and it pulls this reinforcing sheet, two-dimensional sheet, out of the clay. And it's telling us that we need a load of 150 to pull that out. Now I'll explain what this adequacy means later on in the webinar. But this is what we'd expect. Essentially, remember we had a 1.5 meter length of soil embedded in a clay of cohesion 50, and we've got to allow for the top and the bottom of the interface. So we would expect a value of 2 times 1.5, that's 3 times 50, 150. That would be the pull-out force. And the software can also plot out the evolution of the axial force in the reinforcement along its length, which it's done here, so you can see that building up along its length until we get to the end point where we get to 150, and that's obviously the shear force building up as the element is pulled out of the clay. Now, I mentioned earlier that often we use an interface factor with the soil, so that often the reinforcement does not interface to the soil with the full soil strength. So we can add that to the element. So if I click on this element, you can see that as well as the engineering element defined here, we have a potential to define a material on the top and the bottom of the element. At the moment there are no materials assigned, but I can apply material there, which is effectively an interface material, and I've pre-generated a couple of materials here, one called interface above and below. So these materials here, again, if I click on them, the properties appear, and the interface above is defined as what we call a derived Morculo material, and we've basically set it up to have strength that is 0.9, 90% of its parent material, and the parent material, if I click the plus here, is that clay material we've already defined surrounding the block. So essentially, the interface above material has 90% of the strength of the clay there. And I've made another material here just to show that we can model a different strength. This one's got 60% of its parent material, which is this clay. And to apply that to the element, I'm just going to click on the element here, and if I click on this box here, I can change what is there, and I'm just going to select the interface above material, and on the bottom, if I click here, I can add materials, and I'm going to select the interface below. So if I zoom in now on that, you can just see a line above the red reinforcing element equivalent to the interface above, and a shaded line for the interface material below. If I then click solve on that problem again, it will pull out. This time I build up to 112.5 tensile force at the end, and again that's what we'd expect. Previously we had 150, but that was basically a shear strength of 50 times a length of 1.5 at 75, and then times 2 the top and the bottom. Now we have to multiply, instead of multiplying by 2 for the top and bottom, we have to multiply by 0.9 on the top plus 0.6 on the bottom, 1.5, and that gives us that 112.5. Now we can also model frictional properties in the soil and on the interface. I haven't got time in this short webinar to go into that, but essentially the same thing, same principles apply. We can apply interfaces above and below which have different frictional properties, and that will then change the way the shear stresses are transmitted from the soil into the reinforcing element. So we'll jump back to the presentation now. So just to summarize, we can, as you've seen, define interface properties and different ones above and below the reinforcement if we wish, and we'll now look at how that's applied in the example of a reinforced embankment. So when constructing embankments on soft soil, we typically often use a sheet reinforcement to give us that extra strength, extra stability. And the questions we're often going to ask when we're building that embankment is what kind of slope angle is going to be feasible, how strong should that embankment soil be, how high can we build that embankment, and how strong should the reinforcing layer be in order to give us the required strength. Now, a common way you would analyse this is limit equilibrium, which might be a slip circle method using the method of slices, and that works well for certain failure modes, but generally can struggle to capture all types of failure modes, and we'll see a few of those in the demonstration of the software in just a minute. So we're going to jump back to the software and we'll load up this example problem. I think we have here. Okay, so again, we've got essentially half an embankment here. So down here we've got a line of symmetry. We've modelled a embankment using a soil of strength 32, angle of friction of 32, with a small cohesion intercept of half. That's sitting on a soft soil down here with a undrained shear strength of 16. And between that and the embankment, we've got a layer of reinforcement. So we're using an engineered element here. You can see these factors have been set to infinity. We've got a moment of resistance of 0. We specified a rupture strength of 25 kilonewtons per meter and a 0 compressive strength. So these are essentially the three key parameters for the two-dimensional reinforcement. These two values here, or these four values, essentially control one-dimensional reinforcement behavior, and we just set those to infinity. Now, the other key aspect is the interface properties. So again, if I click on this reinforcing element, you can see with the element there, but we've also got a material on the top and the bottom. So on the top, we've got the top boundary material, which again is one of these derived materials, and this one says it's got 80% of the strength of its parent material, and its parent material is this sand that we've built the embankment out of. So effectively you've got an adhesion factor of 0.8 on the top, and then on the bottom here we've got a bottom boundary, and this is also got an adhesion factor of 8, but its parent material is the soft soil with this low cohesion of 16. So that allows us to model the different properties above and below. Now, having set that up, essentially, we just click solve. The software will populate the domain with nodes and find the critical slip mechanism. Now, when we solve a problem, we can ask the software two types of questions, and these are sort of general ultimate limit state type questions. We're always trying to look at the problem for a collapse mode. So what scenario would lead to collapse of this construction? And essentially, there are two ways we can get it to collapse. We can either increase a load on the system somewhere until the system collapses. So for example, we could increase the weight of the embankment, or we could add a surcharge on the embankment and ask the software how big does that have to be to generate collapse. Or we can reduce the strength of the soil. So we have two modes of analysis here. One is factor load, where we have to specify a load that we wish to be increased to drive the system to collapse, or we have factor strength, where the software simply reduces the strength of the soils in the problem until we get collapse. So we're going to run with that particular one, because it's probably more appropriate for this type of problem. And if I just click this button, solve, the software populates the model with nodes and fairly quickly generates a collapse mechanism. So you can see it's a failure mechanism, roughly a slip circle type mechanism with shearing in that circle. And I just magnify that up. You can also see, I'll just slide the animation back. So the animation here is just a guide to show you how the collapse dynamics would occur. But you can see that that mechanism with the soil sliding to the left is generating a tensile force in the reinforcement of around about 25 kPa. So in fact it's utilizing the full specified strength, and you can see that that's falling off to zero towards the free end of the reinforcement, as we'd expect. We've checked that kind of failure mode against the literature, method of slices, slip circle approaches, and we get a close agreement with this factor 1.234, which is effectively the adequacy and strength. If I click this button here, it just gives me a little bit of analysis about how the value's been arrived at. But more particularly, if I click this value here, it tells me exactly what the factoring has done. So in the ground, or in the problem, we've got a soft soil, a sand, a top boundary material, and so on, with different parameters here. These were the values we specified. And in Eurocode terminology, they would be our characteristic values. We can apply Eurocode partial factors to these values before the analysis is done. I haven't got time to go into that, but if we had, these values would be different. And then it's saying if we apply another factor of 1.234 to these values, then we get these values. And it's these values of soil strength that are required for collapse to occur. So that's essentially given us our margin of safety of 1.234. But we can look at other failure modes by changing some of the properties of the system. So, for example, if I make my geotextile very strong, so I'm going to just up this from 25 to 250 kilonewtons per meter, then the software will determine that actually before we get that large combined failure mode, because of the reinforcement that's much stronger, we're going to get to a slope failure on the embankment first before actually failure would occur in the combined embankment soft soil body. And because we've strengthened up that reinforcement, we've now got a bigger factor of safety on the strength of 1.43. And again, you can see the tensile force, axial force in the reinforcement building up, but it's going right up to that 250 value, falling off to this left-hand edge, and the forces that are wanting to cause failure is sliding to the left, are causing that kind of tensile force in the reinforcement. And if we zoom in very closely here, you can just see that at this little wedge here, as it slides is sliding on the reinforcement, but there's no sliding of the soil beneath. So that just shows that we can get sliding on one face only, as well as sliding on both faces. Now, so both of those failure modes still are roughly circular, so are fairly well captured by conventional sort of method of slices slope stability software. However, if we change the strength of this soil here and make that much weaker, so say 8, what we then find is that the embankment, the weight of that embankment causes a squeezing failure on the soil and a kind of extrusion type problem, and that's going to be much more difficult to model using a sort of standard slip circle approach. So again, that just illustrates that the software will seek out the critical mechanism and will not constrain to any particular preconceived slip surface. And then just to wrap up, I'm going to revert the strength of this material back to 16. Now I can do that directly, or we can use the button here just as undo, so that says undo the 8 to 16. So now this soil has gone back to 16. What I'll do is I'm going to change the top boundary and give it a very low multiplier on its strength. So ridiculously low, 20%. It's very smooth interface, just to show that the effect, as we would anticipate, is that we get a slope failure on the top, which is more like a sliding. So the failure mechanism is now quite simple, but it's taking full advantage of the fact that we've got a low strength interface here, so it's just sliding a wedge along here. So we've actually just reduced it to quite a simple 2-wedge analysis. And at this point, our factor on strength, or adequacy strength, has now dropped below 1, which means that the system is not stable as it stands. It actually needs to have material that is stronger in order to stand up. Okay, so I hope that has demonstrated some of the uses of the engineered element in modelling two-dimensional reinforcement. As we're getting towards the end of the webinar, we'll just wrap up with a summary. So hopefully we've shown you that we can generically model two-dimensional reinforcement in LimitState GEO, and we can capture a whole range of different failure interactions with the reinforcement. I've shown you a few calibrations against method of slices and slip circle analysis, so we get a good match for the situations where the dominant mechanism is of a slip circle form. When we're using the software specifically, you've seen that we use what's called an engineered element, and we can specify the rupture strength of that element, and we can define the boundary materials above and below to give the appropriate interface factors. And those are going to be the key parameters that control its behavior, and generally we will set a 0 compressive strength and a 0 bending strength to emulate a flexible geotextile type reinforcement. As I also mentioned, the engineered element is quite a flexible element in the software, and it can also be used for one-dimensional reinforcement. I haven't gone into that in this webinar, but in order to capture the one-dimensional element behavior, we have these additional parameters called pull-out and lateral factors. They can just be ignored when you're modelling two-dimensional reinforcement. The main thing is to set those values to a value of infinity, or 1 to the power of 30 in the software, since you can't sort of set infinity to a computer. So just to wrap up, hopefully what I've shown you is that the modelling of reinforcement in LimitState GEO uses the same mechanics as conventional methods, such as a 2-wedge method, but effectively we can model thousands of wedges and complicated interaction between the reinforcement and the elements, but we're capturing all the conventional assumptions of that type of interaction, but in such a general way that there's no need to separately consider internal or external failure or pull-out lengths or reinforcement rupture. They're all inherently captured within the model. And as you've seen with the general principles of how GEO works, it searches essentially all possible failure modes that are defined by that nodal pattern and interconnecting potential slip lines in the problem, and it will search all of those to give you the most critical mechanism every time you solve. So as you've seen with the reinforced embankment problem, it can capture a range of different failure modes depending on the parameters of the problem. I haven't been able to show you all the features of the software, but hopefully you've got the impression that it's a very easy to use software. You can solve with one mouse click. It's very easy to change parameters. It's also very easy to change the geometry of the problem. And because it solves quickly, you can use it interactively to answer what-if type questions, play around parameters, see what's important in controlling the problem, what is not. And that you can also use the software to solve any ULS problem type. We don't need to impose any idealizations or correction factors for non-standard geometries, and so there's no need to learn all of those and learn many different programs to deal with those different problem types. So I'm going to wrap up there, and I think we've got time for 5 or 8 minutes of questions. So if you have any questions, you should be able to enter those into the webinar interface. Okay, so I've got a question of how we model plant loading on top of that reinforced embankment. So if we jump back to the software, so we've got a reinforcement embankment here. If we wanted to model additional loading on the surface, we can define where that is. So it's usually best to delineate a small portion of that upper surface. So that this is essentially what we call a boundary line. On this blue set of icons here are effectively elements to construct the geometry, and I'm going to use what's here is adding a vertex. That's just allows me to add some extra points on the top boundary, and that means I can now got a cut out bit of that boundary that I can define additional properties. So if I wanted to model a piece of plant there, I can put a load there. So the loads I can apply are listed by Eurocode terminology, and those allow different partial factors to be applied. I'll just put a permanent load in. I'll put a permanent load of 20 kilonewtons per meter squared acting on that surface there. And if that represents whatever a piece of plant or equipment that I've got there, and then I click solve, then the problem will take that into account. Now I think I left this on the previous setup where we had a very low adhesion here, which means that it's going to ignore that, and probably it's not going to make a huge difference because compared to the weight of the embankment, it's not a major contribution. So again, we're just getting that kind of slope failure for factor strength mode. What I'll do is I'm going to make this soft soil, take that back to that low strength of 8, and we're going to get this squeezing failure mode. And what we should see is that the factor has reduced compared to the previous case. I need to, but I think. So what I'll do is I'll just remove that load temporarily, so we've got a benchmark to compare against. So yes, we've got a squeezing failure of this, and we had a factor of safety of 0.97 on strength. In the previous case, when we had the load, the factor had reduced to 0.92, so we'd lost about 5% in terms of safety there. So I put that load back, 20. The other way of using the software, as I mentioned, is in factor load mode, and that allows me to ask a question. For example, how heavy a piece of plant can I put there before I get collapse? And in order to do that, I select the load, and I then stick with that value, but then I have this parameter called adequacy. And if I set that to true, what I'm telling the software to do is to take that load and find out the multiplier on that load required to cause collapse. And if I'm now in factor load mode, I think what I need to do is just check what else have I set adequacy to. So I've set adequacy to the weight of the embankment. Okay, so we can set adequacy on many things and ask the software to look at the factor on the combined loads for failure, but here I just wanted this one. So we go back to that again. Oh, it said it's unstable on its own, which it would be because we've got a factor on the strength of less than 1. So I'll make this soft soil back to its strength of 16. So what it's basically saying is it couldn't do anything to that load. Even reducing it to 0 would have led to inherent collapse because the whole system was already essentially unstable. So now we've got a failure mode which is being driven by this surcharge here, and it's given me a factor 5.654. If I click on that value, what it's telling me is that I specified a nominal surcharge value of 20 kPa, and it's telling me if to get collapse I've actually got to multiply that by 5.6 all the way to 113 for collapse. So that's telling me the magnitude of load there, or the weight of plant I could put there before the system collapses. And that is of course without any partial factors applied or any safety factors applied. Now if I wanted to apply partial factors to that calculation, I could apply, for example, Eurocode partial factors. So I'll just quickly demonstrate that. In the analysis we have what's called a scenario manager, and this allows us to select or define partial factors and parameters. I will pick Eurocode 7 Design Approach 1 Combination 2, which essentially factors down material strengths. Then I can rerun that analysis with those factors pre-applied, and then that's telling me that if I wanted to comply with the Eurocode, I can only get away with increasing that surcharge by a factor of 2.5 rather than 5 before it ceases to comply with the code. Okay, just looking at some other questions. Okay, so I've got a question. Is it possible to use horizontal accelerations by earthquake loading? So the answer is yes. So in this problem, we can apply the pseudo-static analysis approach. If I click anywhere on the blank area of this sheet, I get in the property editor the general project parameters, and one of these at the bottom is called seismic actions. And what I can do is I can apply to the problem vertical and horizontal acceleration. So here, if I put an acceleration of say 0.2, and I can either ask the software what should I multiply that by to cause collapse, by applying adequacy to it, I'm going to just say false. So it's going to apply a constant horizontal acceleration of 0.2. and anything I click on here, there's a little help or a bit of text here explaining what the parameter does, and there's usually a hyperlink to the manual for a more detailed explanation. So again, hopefully that makes the software quicker and easier to use. So we put us in a positive value here, likely to lead to right to left soil movements, which I think is what we want here. So if I click solve on that with that seismic load applied, well, essentially it's telling me that the system is unstable. I'm going to get rid of these partial factors, see if the system is going to be stable, and that again it's unstable, so I think means that that seismic acceleration is just too high to okay, so having reduced it to 0.1, I'm now getting a factor of 2.327 on this surface load. Remember before it was 5, so that horizontal acceleration has reduced the capacity of the system to resist that load. Okay, I've got a question. If I put adequacy on the soil weight, does it apply any Eurocode partial factors to the weight? So the answer is putting adequacy on it doesn't change how partial factors are placed on it. Adequacy simply tells the software whether to use that as part of its way of driving the system to failure. So if you put adequacy on a body of soil, such as I'm doing now here, we're then asking the software how much heavier do I have to make the unit weight of this soil to cause collapse. So I can solve that problem. I'll just remove this seismic action to avoid confusion. So now I've effectively got adequacy on the soil weight and the surcharge. So I'm asking the software how much heavier does the soil have to be and the surcharge to get collapse. So I click solve, and you can see I get a lower number here. And the reason I get a lower number is because the embankment self-weight is much larger and therefore is a much bigger driver of failure than that surcharge up there. But by clicking on this, it's telling me that effectively the unit weight of the embankment has to increase to 28.6 and the permanent load has to go up to 31 to get collapse by that particular method. Now putting the adequacy on the surcharge, or the weight, the weight of the soil, doesn't affect the way the Eurocode partial factors are applied. So generally the weight, the way the usual Eurocode factors are applied are determined by this loading type parameter. So you have a choice of favourable, neutral and unfavourable. So neutral is not a Eurocode term, but in the software it's used just to say don't affect this parameter by any Eurocode factors. So if you don't want the weight affected by Eurocode factors, set it to neutral and they just will not be affected. If you set it to favourable and favourable, then the software will treat it as a permanent load and it will treat it as either permanent favourable or permanent unfavourable, and then it will apply the appropriate factors. So for example, in DA11, permanent unfavourable gets 1.35, permanent favourable gets a factor of 1, and that is where that's going to, how that is applied. So it's not connected to the adequacy, it's connected, as I said, to that or loading type parameter. Okay, I think we've now run slightly over time, so I'm going to pass back to Tom now just to wrap up. But thank you very much for listening, and I hope you found that useful.
Thanks very much, Colin, and thanks to everybody for listening today. We do hope you found the webinar informative, and as I mentioned at the start, if it has prompted any questions, then please do get in touch with us. You can do that via telephone, or if you email info@limitstate.com, we'll be more than happy to answer questions for you. If you'd like to watch the webinar again, or if you think you might know somebody who would be interested to see it, then we'll make a recording available probably early next week, and we'll email you with a link to that once it becomes available online. Please also do look out for the event notifications for other webinars and events that we'll be sending out around via social media and by email later in the year. You can also see on our website LimitState.com/events. And Connie just reminded me there are a few questions that are outstanding that people have sent in. We will try and get round to answering those as soon as we possibly can, so do look out in your emails for those. Lastly, I'd just like to say thanks again to everybody for listening, and we hope that you can join us again for one of our future webinars. Goodbye.